Okay, we've encountered carbocation rearrangements in some of the previous videos, but this one we're going to look at them in a little bit more detail. And specifically, we want to know when carbocation rearrangements occur and when they don't. And so right now we have a secondary carbocation. And so we want to know, can it rearrange to form a more stable tertiary carbocation? So to decide that, you want to look at what are the groups on the neighboring carbon atoms. So we can't have hydride and methyl shifts that are further away than that. And so, right, I identify the neighboring carbons. I see what's on there. So I've got 2 hydrogens to the left and then a hydrogen and a methyl to the right. And I want to determine if shifting one of these groups will give rise to a more stable carbocation. So if I shift one of these hydrogens, right, that's just going to move the carbocation over here. Right, and it's still going to be a secondary carbocation. I don't think that's going to do us any good. Same thing if I move the methyl. Right, if I move this methyl over, right, that's just going to move the carbocation here, but the methyl's gone, so it's still just a secondary carbocation. But if I move this hydrogen, right, if I swap that with the carbocation, that'll put the carbocation here, right, and it'll now be a tertiary carbocation. And so this is the hydride shift that will occur. So to draw that mechanism, I take the arrow from the bond that's connecting the hydrogen to the carbon it's currently attached to, draw that to the carbon that currently has a carbocation. Carbocation moves over here. We now have a tertiary carbocation, which is more stable. Now, not only are tertiary carbocations more stable than secondary or primary or methyl carbocations, but resonance can also help stabilize our carbocation. So in this case, if we undergo this hydride shift and move the carbocation from here to here, it would seem that doesn't get us much, right? Because I went from a tertiary carbocation to a tertiary carbocation. But if the carbocation is here, I can also write the alternate resonance structure, right? Where I have a carbocation allylic to a pi bond, right? So I can move that pi bond over. And so by shifting, I go from a non-resonant stabilized tertiary carbocation to a resonant stable tertiary carbocation that is more stable. And so this carbocation will undergo this shift. All right, so let's look at a couple examples. And so we want to predict whether the carbocation will rearrange, and if it does, we want to draw that mechanism. So I only have one carbon atom adjacent to my carbocation. And it has a pair of hydrogens. If I swap one of these hydrogens with the carbocation, I'll go from a primary carbocation to a secondary. That is advantageous, so this shift will occur. Sorry, this is just a one-sided arrow. Okay, here's another one. And when I look at my neighboring atoms, right, I've got a pair of hydrogens. Actually, I've got 3 hydrogens coming off this one. But I don't think any of these do me any good, right? If I swap this carbocation with one of these hydrogens, I'm going from a secondary to a primary carbocation. So I don't think we want to do that. Now, I've already shown all the bonds here. I don't have any hydrogens, but I do have a methyl group. Right, if I take one of these methyl groups and move it over, then I'll be going from a secondary, right, if one of these is gone, there's a positive here, that would be a tertiary carbocation, that would be more favorable. So I'll draw the arrow from the bond of my methyl group to the carbon with the carbocation. So that hydride shift will occur. All right, here's another example. Now I'm starting with a tertiary carbocation, which is generally stable, but I see this enticing double bond over here. I think if I can move this carbocation down here, then I'll have a resonance stabilized carbocation, which would be more favorable. So what I can do, there are no hydrogens here, but I can take one of these methyl groups, right, and undergo that carbocation shift. And then this new carbocation has an alternate resonance structure. right? So I can spread that positive charge out among multiple carbon atoms, and so this carbocation shift will occur. All right, one final example. So I'm starting with a tertiary carbocation, and it is currently resonance stabilized, right? So I can draw this resonance structure. I can draw two more and move that, right, move these other double bonds around, right, and spread that carbocation around my benzene ring. So because this tertiary carbocation is resonance stabilized, if I were to shift it over here, that would be too far away from the benzene ring for the resonance to occur. And so in this case, we would not expect any rearrangement.